Okay, so welcome to Adventures in Logic for Undergraduates. I'm Harvey Friedman, and this series consists of 5 lectures, and I will, in the announcement for each series, for each one of the lectures, I will give you a pointer to the PDF file of the preceding lectures, so you can look at the PDFs. Video will be available after the lecture series is over. And the lecture series has these topics. First one is today, logical connectives. The second one is logical quantifiers. The third one is Turing machines. The fourth one is Gödel's blessing and Gödel's curse, in honor of Kurt Gödel. And the final lecture is Foundations of Mathematics. And they're all at the same time, 10:30 a.m., and the same room, right here. Now, I'm not expecting you to understand everything as I say it, but I'm hoping that you get the big picture. I try to make this set up so that you get the big picture as I say it. And the details, you can look at the PDFs or videos later. You can look at the PDFs carefully and look into the details. But try to sit back, relax, and try to understand the big picture. Math is much easier to understand from looking and understanding the big picture and then going down from there. All right? So let's start off with and. I want to start off with and. Now, if you don't know what and means, we have a problem, but I'm going to assume we know what and means. This is the starting point. All right, so let's start with this common way of connecting sentences. Mike is a wibble and Jane is a zibble. Now, I don't know about you, but I don't know what I'm talking about, okay? I don't even know what a wibble is, and I don't know what a zibble is. Okay? In fact, I don't even know Mike and Jane. So there's something, though, that I do know about this. There's something I do know. And that is that this sentence, Mike is a wibble and Jane is a zibble. Thanks for coming, and this is the very first page. You didn't miss anything. If you take this sentence as a whole, it's true or false according to whether its two constituents are true or false, even if you don't understand what the constituents mean. So, and is an example of what's called a logical connective. It connects. There are 2 other logical connectives we want to talk about, or and not. So we can have Mike is a wibble or Jane is a zibble. Now again, this sentence taken as a whole is true or false according to whether its two constituents are true or false. We can also consider Mike is not a wibble. Mike is not a wibble. This sentence taken as a whole is true or false according to whether its one constituent is true or false. And what is its constituent? Mike is a wibble. Now, what is the rule that determines the truth value of these 3 example sentences in terms of the truth values of their constituents? What is the rule? And by the way, I use the word truth value. I just mean T if it's true and F if it's false. Okay? As I said before, a number of people came in. I'm hoping that you can understand the big picture of what I'm talking about. For details, you'll see the PDF files after the lecture. I'll give you a pointer in the next announcement for the next talk a pointer to the PDFs of the previous talk so you can really examine this stuff carefully, okay? So what are the rules for and, or, and not, or so-called truth tables? So let's use letters for the constituents. So we write A wedge B, or A and B, for and we write A or B with a sort of a big little V, right, for or, and we write squiggle for not A. So those are the three sentences that I was talking about before. Mike is a wibble and Jane is a zibble. Mike is a wibble or Jane is a zibble. Mike is not a wibble. So you see, those are the three patterns. A and B, A or B, and not A. Now, there are four possibilities for A and B, right? A and B, each one of them can be true or false. And there are four possibilities. And you see the columns A and B. This is how truth tables are written. TT, TF, FT, and FF for the A and the B. These first two columns. And then A and B, well, what is that going to be? Well, true and true is going to be true, right? True and false is going to be false. False and true is going to be false. False and false is going to be false. Now, what about or? Or is obviously more lenient. True or true is true. True or false is true. False or true is true, and false or false is false. And what about not A? Not A just flips the T's to the F's and the F's to the T's. So not T is F, and not T is F, and not F is T, and not F is T. Notice not A has nothing to do with B, right? But nevertheless, it's convenient to put it on the same table. So there's a combined truth table for three statements, A and B, three formulas, A and B, A or B, and not A. Call them formulas. Okay, I think you at least understand the big picture, and for those of you who've seen anything like this before, this is clear. Okay. All right. So now let's talk about logical equivalence. Two formulas are said to be logically equivalent, and that's written with a triple bar, if and only if they have the same truth values under the same assignments of truth values to their aggregate letters. Here's an example, a slightly complicated example. A little bit complicated, not too complicated. A and B, I claim, is logically equivalent to B and A or C and not C. Because if you assign the 8 possibilities to A, B, and C, 8 possibilities, right, you will find that they come out the same. And you can work that out on your own or just think about it. Because if you or with something that's ridiculous, like C and not C, then it doesn't count. You get to think that way. And then B and A should be the same as A and B, because and is, as you know, pretty commutative, right? So you can sort of believe that, but you can also check it in the truth table. Okay, now here's two others that are more important. That's a sort of an artificial one. A or B is logically equivalent to not of, left parenthesis, not A and not B, right parenthesis. And A and B is logically equivalent to not of, left parenthesis, not A or not B. Okay, you can ponder that on your own when you see the PDF file. Okay, now by the word challenge is a nice polite way of saying homework if this was a course. Okay, so challenge, and by the way, the challenges range from quite easy to quite difficult. So you know, there's a whole range of things here. Every propositional formula in not and or is logically equivalent to one in not and. And every propositional formula in not and is logically equivalent to one in not and or. And you can prove that by if you're inclined to give rigorous mathematical proofs, you can prove this by induction using those two laws. Okay, but nevertheless, this is sort of believable, because what I did is I wrote or in terms of and not, didn't I? With this first logical equivalence. And I also wrote and in terms of not and or. So this is very plausible. Now, to actually turn this into a proof requires some finesse, but nevertheless, it should be clear. The big picture is clear? Okay. All right. Now, we've been using the connective set not, and, or. Now, this set is considered to be logically complete. By the way, that's a positive attribute. Logically complete, it's good to be logically complete, in the following sense. Suppose, let S be any set of assignments of truth values to the letters A1 through AN. Then I can cook up a propositional formula using not, and or, and A1 through AN, which has truth value T under exactly the assignments in S. In other words, I can get any, here's the big picture. I can get any behavior that I want. Any behavior that I want. Behavior meaning under which conditions does the thing come out true and when does it come out false. Okay? That's what I mean by behavior. I don't necessarily mean whether the formulas are angry or not. I just mean, just that, okay? All right. Now, because of the reductions from the last slide, we conclude that the connectives not and or, and also not and are also complete. Because anything you can do with the three, you can do with those two. Now, the connective set or and itself without the not is not complete because every propositional formula using or and A is going to come out true under some assignment. It's always going to come out true. You can check that. Now, challenge. Prove everything I just said. Okay? Prove everything I just said. Okay? Well, you may or may not be able to do that so easily, and you'll certainly want to look at the PDF file, and I don't expect you to do that right here, since there's another 1,000,000 slides. But nevertheless, you get the big picture. Now, math needs and uses more connectives. You can't do math with not, and or unless you have the brain of a machine. Okay, so it turns out from experience that you need a little more flexibility, not because there's something missing in not, and or, because it is logically complete, right? It is logically complete, but in order to think properly, we seem to need something else. Two other things, one super important and one somewhat important. The first one we need is a concept of if-then, or implies, because math is just full of that kind of thing. This implies this. And the other thing is if and only if. So you've seen these things, if-then and if and only if. And they are also connectives, just like the other things are connectives, and therefore they have a truth table. The truth table is as indicated in the display. And I should point out to you that if A then B, or A implies B, comes out false if the front is true and the back is false, which gives a lie to the if-then, right? Because if the if is true and the then is false, that gives a lie to the if-then. And it's considered true otherwise. Now, some people find this counterintuitive, but we know that this is the only way to look at the way this is the way that mathematics operates, and we cannot have a different setup. Okay. Now, if and only if is just what you'd expect. If and only if it comes out true, just in case both the front and the back are the same. All right? Okay. So we have, mathematics is based on 5 connectives. Not, and, or, if then, if and only if, or implies if and only if. Now, math also desperately needs more than this, but that's for the second lecture. Mathematics desperately needs something unbelievably more subtle, which is it needs for all and it needs there exists. Okay, but before we get to that, this subject called propositional calculus or logical connectives is a subject in its own right that we'll adhere to today. Okay. All right, so we have not, and, or, implies, and if and only if, and we proceed, and we call these satisfiers. So if I set A equals T and B equals T, that's an example of a satisfier for A implies B. A satisfier, let's call it. I mean, there are other names that are used, more clumsy names like satisfying assignments and so forth, but I'll call them satisfiers, all right? Now, I don't want you to read this. I just want you to absorb there is such a thing. So you can have a very complicated formula instead of these little ones that I'm talking about. And I made this up just for you. Actually, I see a little bug because I wasn't going to use the double arrows here. Double arrows is used for another purpose. And so that double arrow should be a single arrows. That's an error on my part. This double arrows on the first displayed line there. Okay, so I considered the following satisfier. I claim that A equals T, B equals T, C equals false, D equals true, E equals false is a satisfier for this. And you can do this by a nice computation, which we would rather have a computer do, and a computer can do extremely efficiently, which is we actually evaluate each of the subformulas, so to speak, hierarchically inside up. Sort of the least complicated out to the most complicated, you see? And this, also is, you can write, if you're a programmer, you write these formulas as trees, and you start assigning T's and F's to the things starting at the leaves down. Starting at the leaves of the tree down, for those of you who are computer-oriented people, all right? So that's just the one particular row of the entire truth table, and it's not spread out because I don't have enough space, right? It's sort of chopped up. All right. Now, also implies can be written in terms of or, and if and only if can be written in terms of not, and or can be written in terms of implies, and so forth. And I did a few of these. So A implies B is logically equivalent to not A or B, which you could check by a truth table. And A if and only if B is logically equivalent to either A or B or not A and not B, which is intuitively clear and which you can check. And then A or B is equivalent to not A implies B and so forth. There's a number of things like this. And since those are logically complete, we know that not and implies is also logically complete, right? Because from the last one, we know that we can get or from not and implies. So we get or from not and implies, and since not and or is complete, not and implies should be complete. Okay? Challenge. There are 32 subsets of these 5 connectives. Tell me which ones are logically complete. Which sets of connectives are logically complete? Which sets? Okay, there's a little challenge for you. You have to do some interesting things to completely solve that problem. You don't mind doing interesting things, so it should be fun. All right? Tautologies and contradictions. Look at these 3 things. A or not A implies A if and only if A. All 3 of these things come out true for all truth assignments to A. By the way, how many truth assignments are there to A? 2. Making it T or making it F, right? So this is very easy to check. Okay? Now, here's a more sophisticated example. A implies B, parentheses implies A, parentheses implies A. This comes out true for all truth assignments to A and B, turns out. Okay, you can check that, even though it's kind of weird. And now this one, A and not A, and also A if and only if not A. These come out false for all truth assignments to A. These come out false. Okay, now let's step back and say what we're doing. A tautology, this is a nice word. A tautology is a propositional formula whose truth value is T under all assignments of truth values to its letters. under all assignments of truth values to its letters. A contradiction is a propositional formula whose truth value is F under all assignments of truth values to its letters. Now, most formulas, of course, are not going to be in either category. This is a rather special thing, right? Now, the tautologies, so to speak, like on the first line or the first row are tautologies. The tautologies are these good ones that are kind of always true, so to speak, quote unquote, always true, okay? You have confidence in tautologies, that's the point. All right, now, there's another notion called satisfiable. A propositional formula is said to be satisfiable if and only if it has some satisfier, i.e. its truth value is T under some assignment of truth values to its letters. Some, not all, just some. All right, now life can be very difficult to determine this, but there are a lot of letters. For example, here's a formula I made up. Has got a lot of letters. It's got 6 letters, so there's 64 rows in the truth table. And if I gave you one with 1,000 letters, the truth table would be absurdly long, right? You wouldn't be able to, in the universe, there wouldn't be enough space to give the truth table. So now, first of all, let me state an easy challenge. Any way of determining whether a propositional formulas are tautologies can be easily converted to a way of determining whether propositional formulas are satisfiable and vice versa. I leave that to you to ponder, that there is an easy way of going from one to the other. I mean, you have to do something. You just can't stare at the formula and say, well, it's satisfiable, therefore it's a tautology if it's blue. I mean, you can't do it that way. You have to actually do something clever, but not too difficult. Okay? All right. $1 million. Most students are interested in getting $1 million, particularly if it's not too hard to do it. So, unfortunately, this is the problem. This is going to be hard. Okay, the obvious foolproof method for determining whether a propositional formula is satisfiable is by merely, quote unquote, trying all possibilities. Right? Blindly. This could take an exponential amount of time relative to the size of the input formula. Because if it's a big formula, it's probably got a lot of different letters in it, right? You're going to have a huge number of assignments you have to test, unless you get lucky, right? All right. Can this be done? Can this be done by a more clever method that uses at most a polynomial, not exponential, amount of time relative to the input size? For example, it's maybe quadratic in the input size, or something like that. Well, the method, by the way, is required to work flawlessly for all propositional formulas. This is a requirement. Not most of the time, but flawlessly all the time, okay? That's the problem. Now, a proof of this one way or another wins a $1 million check from the Clay Foundation, and you can Google it and get the terms of the $1 million. Now, I want to warn you, there are easier ways to make a living, like throwing 100-mile-an-hour baseballs or hitting them out of the ballpark. Not too many people can do that either, but more can do that apparently than can do this, which is 0 right now. Okay, so I'm warning, this is not the easiest way to make a living, but I just offer it to you as a possibility. Okay, all right. So formula alpha logically implies formula beta, so we're going to talk about logical implication. If and only if any truth assignment to the aggregate of letters making alpha true also makes beta true. And we write this as alpha double arrows beta. Don't confuse that double arrows with the connective arrows, which I made a mistake in the other slide I told you. All right, so there are a bunch of basic facts about this that are very worth knowing. Alpha logically implies beta if and only if the formula alpha arrows beta is a tautology. Also, alpha is logically equivalent to beta if and only if alpha logically implies beta and beta logically implies alpha. And also, alpha is logically equivalent to beta if and only if alpha, if and only if beta is a tautology. So this is worth thinking through. And also, logical implication is reflexive and transitive, but not symmetric. And logical equivalence is an equivalence relation, i.e. reflexive, transitive, and symmetric. Reflexive, transitive, and symmetric. Challenge, prove all these things. Okay? All right, I hope you're still with the big picture. Okay. All right, here's another big picture item. These connectives act like addition, multiplication. They have some vague relationship, which is not exact, with ordinary arithmetic and algebra. In other words, there's a commutative, associative, and distributive law for these things. A and B is the same thing as B and A, logically equivalent to B and A. Those are the commutative laws. The first line is the commutative laws for the three connectives and, or, and if and only if. The second line is the distributive law for and or. No, associative law for and. The third line is the associative law for or. The fourth line is a little strange, but it's the associative law which works for if and only if. The fifth line is the distributive law. A and B or C is equivalent to A and B or A and C. And this is very much like arithmetic or algebra. A times B plus C equals AB plus AC. Very similar in nature. Because the closest thing and is like is multiplication. And the closest thing or is like is plus addition, but there are differences. Now, but also we have, in logic, we also have this other distributive law. A or B and C is logically equivalent to A or B and A or C. And that's like A plus BC equals A plus B times A plus C. Now, I hope you're not one of these people who actually likes this one too, because, you know, this is not right. A plus BC equals A plus B times AC, but it's very cute. Okay. All right. Now, all these laws here hold no matter what propositional formulas we plug in for the letters A, B, and C, as long as we substitute the same formulas for the same letters. In logic, this occurs very often. This is called substitution. You got a situation where you have some letters, and you can replace the letters by complicated formulas as long as you replace the same letters by the same formulas. Very often, this also works when the original thing works. And in this case, this is a case of that. Okay, it's also very convenient to put an arbitrary propositional formula in a standard form that you can more easily work with for some purposes. And first of all, by associativity, commutativity, we can speak freely of disjunctions of formulas and conjunctions of formulas. And also, let me mention what a literal is. A literal is defined to be a letter or a negated letter. You either have a letter or you put a not in front of a letter. That's called a literal. It's called a literal in logic. A formula is said to be in disjunctive normal form if and only if it is a disjunction of formulas, each of which is a conjunction of literals. So we have this theorem that every propositional formula in our 5 connectives is logically equivalent to a formula in disjunctive normal form. And this is harder. This is starting to get a little harder to. This is a nice, harder homework. And I want you to prove this, if you can, using satisfiers. You'll find it very satisfying.
I guess I missed, what exactly was a disjunction and a conjunction?
Oh, or a disjunction means ors, and a conjunction means ands.
Oh, okay.
Yeah, disjunction means or, and conjunction means and. The other way is conjunctive normal form, if and only if it's a conjunction of formulas, each of which is a disjunction of literals. And every propositional formula in our 5 is logically equivalent to a formula in conjunctive normal form. And prove this using satisfiers. All right, now I want to talk about something a little bit more abstract mathematically. And pretty interesting. So far, we've been talking about satisfiability of an individual propositional formula. We now want to consider satisfiability of sets of formulas. Sets of formulas. And there may be infinitely many formulas. Now, what do I mean by satisfiability of a set of formulas? I mean that there's a single assignment of truth values, i.e. a satisfier, that makes all of the propositional formulas in the set true at once. Simultaneously all come out true. And let's assume we have a fixed alphabet of distinct letters, A1, A2, A3, ... for use in propositional formulas. Now, the satisfiers consist of the assignments of truth values to all of the letters. Thus, the satisfiers may assign truth values to letters that don't occur in the set of formulas. This is very convenient and doesn't affect anything. Okay, so we're going to take a satisfier to be where you assign a truth value to every letter, even if the set of formulas is missing letters. And obviously, the letters that don't appear, we don't really care what they're assigned. It turns out that it doesn't make any difference, right? Because we don't use that assignment. All right, now we've got this thing set up so we can state this theorem called the Compactus Theorem. And I want you to get the big picture of how this is proved, because it's actually pretty interesting. A set S of propositional formulas is satisfiable if and only if every finite subset is satisfiable. Okay? A set of propositional formulas is satisfiable if and only if every finite subset is. Not at all obvious. Okay? For this interesting proof, assume that every finite subset of S is satisfiable. We want to show that S is satisfiable. All right? So we're going to have to pretty much construct a satisfier of all of S simultaneously. Now, we just have satisfiers for pieces of S. So how do we put them together? It's not so clear. All right. I make the following claim. Every finite subset of S has a satisfier which assigns T to A1, or every finite subset of S has a satisfier which assigns F to A1. One or the other. Prove this claim. You have to assume the claim is false and derive a contradiction. Okay? And in fact, we know that you must use proof by contradiction here. There's no way to do this directly. There's in fact a part of logic called when can you prove things directly and when can't you? There's a whole subject like that, which is a bit too advanced for this lecture series. But there is such a subject. Okay. All right. So now where are we? We have the following situation. And I call this, let's call this a partial satisfier. Call this F1 is a partial satisfier. And it only assigns to A1. It only assigns to A1. And we have that every finite subset of S has a satisfier extending F1. That's what we have here. Now, I just want you to get the big picture of this proof, not the details, because details might be a little hard to sit down and listen to. Every finite subset of S has a satisfier extending F1. That's what I said. Now, I'm going to go further. I claim that every finite subset of S has a satisfier extending F1 that assigns T to A2, or every finite subset of S has a satisfier extending F1 that assigns F to A2. Okay? Challenge, prove this claim. Now, you actually do this the same way. You assume the claim is false and derive a contradiction. Okay, this gives us a partial satisfier F2 extending F1, which assigns only to A1 and A2. Every finite subset of S has a satisfier extending F2. Continuing this way, obtaining an infinite series of growing partial satisfiers. The union of all of these partial satisfiers gives us a satisfier for all of S. Okay. So that's how we do this. Okay. All right. So now let's talk about logical implications. We now consider logical implications of infinite sets of propositional formulas. Okay. logical implications. Let K be a set of propositional formulas, and let A be a propositional formula, all in our 5 connectives. Okay, we say that K logically implies A if and only if every satisfier of K is a satisfier of A. So we say that K logically implies A if and only if every satisfier of K is a satisfier of A. This is a generalization of what we were saying before. And we write K double arrows A. And so this theorem says that if K logically implies A, then some finite subset of K logically implies A. If K logically implies A, then some finite subset of K logically implies A. And the proof goes like this. Suppose K logically implies A, then K together with not A is not satisfiable. Check that on your own. By the Compactus theorem, K naught together with not A is not satisfiable for some finite K0 contained in K. Check that on your own. And therefore, K naught logically implies A. Check that on your own. These are very easy to check once you think about it. So in other words, you can get this theorem from the Compactus theorem by just simple manipulations without having to do any hard work. That if a set of formulas logically implies a single formula, then some finite subset does. Okay, and finally, the last topic I want to talk about for a while is axioms, axiomization and axioms. It's common in logic to provide axioms and rules of inference that yield exactly some important class of formulas. There are several types of such formal systems, and I just want to talk here about one type. And we want axioms and rules of inference for proving tautologies in some chosen set of connectives. See, the tautologies are the things you should have great faith in, right? Because they're always true. But you want to prove tautologies. Okay, so I'm going to talk about what's called a Hilbert-style axiomatization of propositional calculus. Now, in a Hilbert-style axiomatization of propositional calculus, we choose a finite set of formulas in some chosen set of connectives as the axioms. And then we use the following 2 rules of inference. The first is any substitution instance of any axiom is considered derived, as long as we stick to the connectives we chose. Any substitution instance of it. So for example, if I wrote A arrows A as one of my axioms, then I would allow, then any formula alpha arrows alpha is immediately considered derived. The second thing is a special rule called modus ponens, which goes like this. If alpha and also alpha arrows beta have been derived, then beta is considered derived. And that's called modus ponens. Okay, that's the kind of architecture that a Hilbert-style axiomatization of propositional calculus has. And such a system is said to be sound if and only if every formula that's derived is a tautology. So soundness means it's remotely reasonable for the purpose at hand. We certainly want it to only generate tautologies. And it's said to be complete if and only if every tautology is derivable. It's complete if and only if every tautology is derivable. Okay? And of course, we would want this to be both sound and complete. We want to be able to derive exactly the tautologies. Okay, and there are sound and complete Hilbert systems for all 5. Now they're somewhat cluttered. I will display one, but it's typical to focus on a simpler case, which is just not and implies. Now if you remember, not and implies is a logically complete set of connectives. So this is not such a bad choice. Okay? Now here is a famous set of 3 axioms. The first one is A implies B implies A, and the second one, think of the second one as formalized modus ponens. Because if you cancel the A, what do you see here? You see B implies C, and you see a B, and then you see a C, right? And then you have sort of A as an hypothesis. So this is not a completely crazy thing, the second one. And the third one is also kind of says that if there's something wrong with not A, then A must be true. If not A is false, then A is true. Because not A is going to be false if you can get both B and not B. But those are intuitive ideas. Okay, these are the formal axioms that Elliott Mendelsohn uses, with a substitution that I mentioned, and with the modus ponens. So you're allowed to make substitutions in those three, and you're also allowed to do modus ponens. You're allowed to make substitutions only for those three things, and you're allowed to do modus ponens. Okay, challenge. So in this book, which has a second edition that's more recent, has a proof of soundness and completeness of the above axiom system. Also, you can look at this in Wikipedia. You can look up list of logical systems, where it cites Lukasiewicz for using the following simpler third axiom. So the third axiom is neater, and also this is also sound and complete. So challenge is to prove soundness for these two systems by induction. In other words, show that everything you get out of this is a tautology, okay? And that's the easy part of things. But I leave that to you. And now how do you do completeness? Well, completeness for such systems is much harder. Search that every tautology is a theorem. And the way this is done is actually, it's a fairly elaborate thing to do. First, you carefully define proofs as finite sequences of formulas, each of which is either a substitution instance of an axiom or follows from previous entries in the finite sequence by modus ponens, just according to the way I set it up. But you actually talk about proofs as sequences of formulas. Okay. The next step is to extend this definition of proofs to proofs from a set of assumptions. Suppose I have a set of assumptions, maybe completely bogus, I don't care. Suppose I have a set of formulas called assumptions, then I can do proofs relative to that. You have to define that carefully, what you mean by that. You're not allowed to apply the substitution rule just to the axioms, not to these assumptions. But everything you can apply modus ponens to. And the assumptions are in there for free. Okay, so there is this notion. And then you prove a theorem called the deduction property. This is very important. It's called the deduction property, sometimes called the deduction theorem. It says that if a formula A can be proved from S together with B, then B implies A can be proved from S alone, where S is a set of assumptions. If A can be proved from a set of assumptions S together with B, then B implies A can be proved from a set of assumptions S. You have to prove that. Now, prove the deduction property for these two systems. This is a little tricky. Use induction on the lengths of proofs. Another challenge, finish the proof of completeness for these two systems using satisfiers. And that you'll need some other, several ideas that I haven't mentioned to do that. Okay. You can find these things in the books, too. All right. Now, what if that's just for not and implies. What if I want to do it for all five? So if you want to do it for all five, you start with the three, and then you put two things down there to make sure that if and only if behaves right. Three things. The next three lines are that if and only if behaves right. And the last two lines are the definition of and or in terms of arrows and not. Okay. And then you use substitution for the axioms and modus ponens. And challenge is to prove soundness for the system using induction. Now, to prove completeness, there's a trick to this. Suppose you have any formula at all. You can prove completeness for this system that I described, this complicated one. You can prove that this is complete using the fact that that one's complete. In other words, you can reduce it so you don't have to do as much hard work. And the trick is this. Suppose I have a formula involving the 5 connectives. then let's call it A. Then A star is obtained by replacing and, or, and if and only if with not and arrows by their definition. Remember, I defined and in terms of not and arrows, and I defined or in terms of not and arrows, or should have, and I defined if and only if in terms of not arrows, or I should have, I could have, okay? Because it is complete. And then you make those substitutions, so you reduce the formula to just not and arrows, and the claim is that this will be logically equivalent, and then you want to prove that they're interprovable from each other, that they're interprovable from each other in the big system. And then you can finish the completeness proof. Okay? So that's more or less, roughly speaking, how that works. And I did promise when I set this up that I would quit at 48 minutes, which is, what is that? That should be about now. It should be 18 after, right? So we've got about 30 seconds or something like that. Is the bell supposed to ring around here? I think it probably will. But nevertheless, I think it's another minute or something. So I can take questions, and I do want to end, more or less now. But I can take some questions if you want to ask me something. No questions. Ah, good.
So when you were first talking about sets of formulas, you had the assumption that we use a countable number of truth assignments, and I was wondering if anything more can be added by extending that to, say, an uncountable set of truth values.
Okay, so I decided I wasn't going to talk about that in the main lecture because a lot of people aren't familiar with set theory. But the answer is yes. In other words, what I've been talking about here in that compactness theorem, for example, is everything was local here except the compactness theorem. Everything else doesn't make a difference how many letters you have, because I was talking about individual formulas, which have to be finite, right? We're talking about finite formulas. But I think you're talking about the compactness theorem when the number of letters is arbitrary, not just countable. Is that correct?
Well, I was just wondering if there are different consequences for choosing a countable set, but yeah, I also was wondering if the compactness theorem breaks down under some...
The compactness theorem holds no matter what set of letters there is, no matter how large. The proof requires transfinite induction, not induction. So in the proof that I gave, this was an inductive process where I built bigger and bigger finite, partial satisfiers. So if I were to want to do this for arbitrary sets of letters, I would need a transfinite construction, and that works. And we do know that the axiom of choice is needed to prove this for arbitrary sets of letters. Does that help?
Yeah. So I guess just to finish that up, is there any way to break the compactness theorem? Sort of. It's the question. Like maybe building a completely different logical system.
Well, there is a subject called infinitary logic, in which you're allowed to take the conjunction of infinitely many formulas at once. Alpha 1 and alpha 2 and alpha 3, ... all at once. Now, you might say, what has this got to do with logic? Well, it's abstract logic. It doesn't have anything to do, or much to do, with logic as humanly practiced, because people don't usually have the time to write down infinitely many conjunctions, right? But nevertheless, there is this subject. It's called infinitary logic, and compactness theorem fails miserably for that logic. Okay, does that help? So these were very good questions. Do you have any more good ones, or even bad ones? No? Yeah.
I got a bad one.
Okay.
When are the videos going to be available? Because I'm going to miss the next 4 lectures.
PDF files will be linked to in the next announcement for the next talk. and they will be probably on my website under lectures, but I will put the link out and put it up there. That's PDF files. Movies, you have to wait till the end of the 5 lecture series for the movies. But you know, I didn't notice anybody really leaving at 18 after. I just wonder if I should. You think I can? I don't know if I should make this stretch this to an hour. What do you think? I would think that that's a little risky. I'll have to ponder. Okay. All right. Thanks for coming. I will see you if you want to next week.